Hi everyone, welcome to Data Nutshell. So far we have seen RAID 3, that is byte level stripping with dedicated parity, and RAID 4, that is block level stripping with dedicated parity. Now we move to RAID 5, one of the most popular RAID levels in history. What makes RAID 5 special is that it eliminates the parity disk bottleneck. How? By distributing the parity across all disks so that all the pressure of updating those parity values does not come to one single disk. This removes the bottleneck that we saw in RAID 3 and RAID 4. So, this made it a go to choice for balancing performance, reliability, and storage efficiency. Today, we will see how RAID 5 stores data, how distributed parity works for RAID 5, the performance characteristics of RAID 5, and why RAID 5 became so widely used. So let's see how RAID 5 works. RAID 5 uses block level stripping like RAID 4, but instead of a single parity disk, it distributes parity across all disks. Let's take an example. Say we have three data disks and one parity disk. Let's see how it works in case of RAID 5. Say for the first iteration, our disk 1 is acting as the parity disk. So when data block A1 comes, it goes to disk 2, data block A2 goes to disk 3, and data block A3 goes to disk 4. And the parity of these three blocks is stored on disk 1. Then for the second iteration, let's say that disk 2 is acting as a parity disk. So when B1 comes, it goes to disk 3, B2 goes to disk 4, and B3 goes to disk 1, and the parity of B1, B2, B3 goes to disk 2. Then for the next iteration, disk 3 will act as the parity. So C1 will go to disk 4, C2 will go to disk 1, and data block C3 will go to disk 2. And the parity of C1, C2, C3 will go to disk 3. Then for the next iteration, disk 4 will act as the parity. So D1 will go to data disk 1, D2 will go to disk 2, D3 will go to disk 3, and the parity of these three blocks D1, D2, D3 will go to disk 4. That's how RAID 5 works. So we saw that for RAID 5, parity rotates across disks. For iteration 1, disk D1 acted as parity disk. For iteration 2, D2 acted as parity disk. For iteration 3, D3 was parity disk. For iteration 4, D4 was parity disk. And then it would repeat again from D1, D2, D3, D4. So any single missing block can be reconstructed via the XOR of the other blocks. So just like RAID 4, RAID 5 uses XOR for parity. So the parity is XOR of all data blocks for that iteration. So for the parity value for the first iteration will be A1 XOR A2 XOR A3. And if one disk fails, the missing block can be reconstructed using that parity value and the remaining blocks. So for the first iteration, what we saw was that A1 was sitting on disk 2, A2 was on disk 3, A3 was on disk 4, and the parity value sat on disk 1. So say disk 2 fails, you will lose block A1. But block A1 then can be recalculated using parity and the remaining blocks A2 and A3. How? As we know that parity was A1 XOR A2 XOR A3. Now since we lost A1, A1 can be calculated as P XOR A2 XOR A3. Performance characteristics of RAID 5. The strengths are balanced performance and storage efficiency. So let's look into performance. Read operations are fast because data is stripped across disks. And write operations are faster than RAID 4 because the parity isn't centralized on one single disk. So it removes that bottleneck of having to do all the parity operations on one single disk since the parity is spread across multiple disks. Is it efficient storage wise? Because only one disk worth of capacity is used for parity. For example, out of 4 disks, we can keep 3 disks for data, and only one disk has to be reserved to store parity values.